Good morning, Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. So today we are going to conclude your chapter 13. We are going to focusing on the halogenations of alkane to produce alkyl halides. Regarding these halogenations, in the last class, in the very end of our last lecture, we mentioned that you have 4 different types of reactions. Your alkane can react with your fluorine to produce fluorohalides, fluoroalkyl halides, and hydrogen fluoride. So this reaction is very explosive. Therefore, we barely use this method to produce halides. So second reaction will be chlorination. So RH alkane reacted with Cl2 to produce RCl and HCl. So this chlorination is an exothermic reaction. It's very useful for most of cases to produce different replacement of halides. And the third reaction will be bromination. So it's RH reacted with Br2. So you produce RBr and HBr. This reaction is also very useful and is an exothermic reaction as well. So the last reaction will be reacted with iodine. Your alkane reacted with iodine. So this reaction is an endothermic. Usually it's not very feasible for us to produce alkyl halides. So we are mainly focusing on the chlorination and bromination. First example related to the chlorination of methane. In the industry, the very important reaction carried out at high temperature 400 Celsius is through methane reacted with chlorine. So you produce 1,1-chloromethane, 2-chlorodichloromethane, trichloromethane, and tetrachloromethane. So this reaction is going through the radical reactions. You are going to find the radicals as intermediate. It's different from your carbocation. It's through the radical. What do you mean by radical? Radical refers to the species which contain the unpaired electrons. Commonly radicals or commonly free radicals are found to be such as oxygen molecule. You have your oxygen molecule, you have two different electrons, they are unpaired. Your nitrogen dioxide, so this dioxide, this nitrogen is more positive, and your nitrogen monoxide, you have 1 electron which is not paired. So also these free radicals, due to the unpaired electron existence, make this radical very unstable. This radical in terms of carbon, you also have primary, secondary, tertiary carbon. Again, depending on how many this radical carbon connected to the number of other carbons. Primary radical meaning the carbon with an unpaired electron connected to another carbon. If you have methyl CH3 dot, this dot radical using a little dot to represent it, they're called methyl radical. And you have primary radical, you have secondary radical. In your secondary radical, the carbon with unpaired electron is going to be connected to other 2 carbons. Similarly, tertiary radical refers to the carbon with unpaired electron connected to some other 3 carbons. The stability of these radicals very similar to your carbocation, also related to the substituents. The more substituted groups or radicals are more stable. The more substituents you have in your radical, the more stable this radical is. Therefore, your tertiary radical compared with your secondary radical is more stable. Methyl radical is the least stable radical, and then followed by the primary radical, and then secondary radical. The tertiary radical is more stable. When we discussing stable or not, is compared, it's relatively compared with your radicals, not compared with your compound. So what you also see, you can use the spin density, so which in yellow, so is shared into the connected alkyl groups. If this density of electrons can be shared with other alkyl group, so the electron or the unpaired electron, the more negative nature is going to be delocalized, meaning more substituted radical or more stable species. Regarding this radical formation, we need to learn bond cleavage. Bond cleavage has two different types. One is called homolytic bond cleavage. Second one called heterolytic bond cleavage. The homolytic bond cleavage refers to each atom is going to retain one of the bonding electrons. Your bonding electrons refers to two electrons. So I have imagine my hand is one carbon, another carbon. Each of my finger represents an electron. So two carbon form a bond by sharing two electrons. In the homolytic bond cleavage, so each of the electron will be retained by each of the carbon. In your heterolytic cleavage, the element with higher electronegativity will retain both bonding electrons. Again, this is a carbon, this is a chlorine. If the bond cleavage occurs, both of the electrons will go to your chlorine, will go to the more electronegative element. So the energy will be required through this bond dissociation. So it's called bond dissociation enthalpy. Bond dissociation enthalpy also can be used for us to measure the bond cleavage or the bond strength. The stronger the bond is, the more energy required to break it up. So how do we denote or express the homolytic bond cleavage? Usually you use a single hooked or single-headed arrow to represent the electron movement. If you have x, y, you share two electrons between x and y. One electron will be moving, will be retained by x, another electron retained by y. You form x radical and y radical. So in your heterolytic bond cleavage, imagine your y is more electronegative with higher electronegativity. X has a lower electronegativity. Therefore, during the bond cleavage, these two electrons will be retained by your y. Therefore, your y become negatively charged ion, your x become positively charged ion. So this case, you use a double-headed or double-hooked arrow to represent two electron transfer from the bonding to one of the atom. So that atom has a higher electronegativity. So let's see, for our alkane, so you have, say, for example, you have a 1-methyl 1,2,3 propane, you have a 2-methyl propane. What's going to happen? Let's see how many different types of carbon we have. So this end carbon, this carbon connected to one hydrogen, and the second carbon connected to another hydrogen. Therefore, you have two different types of carbon. You have a secondary, you have tertiary carbon. If your secondary, tertiary, and you also have this carbon, which is primary carbon. When you lose one hydrogen, this hydrogen and carbon, let me call it carbon 1. Carbon 1 and hydrogen, they subject to the bond cleavage. So this species, this carbon-contained species, retain the one electron, become a radical, and then you have your hydrogen radical. What we found, the bond dissociation energy, enthalpy, which is positive 422 kilojoules. And if you remove this pink colored hydrogen, which connected to the tertiary carbon, so you form a tertiary radical. The first one, you form a primary radical. So which one do you think is most stable? So based on this dissociation, this bond dissociation enthalpy, So the one with smaller dissociation enthalpy usually refers to ED to be formed. Therefore, this tertiary radical is much more stabilized compared with the secondary or primary. Tertiary radical is more stable. Also, you can use this diagram to represent the energy and potential energy graphs of different kind of bond cleavage. Again, to summary, so the less the energy, the more stable the related radical is. Usually, primary is least stable and secondary is better. The tertiary is much more stable than the other ones. Your methyl radical is the least stable one. So we are going to use the methane reacted with chlorine. So methane reacted with chlorine to produce chloromethane and further dichloromethane, tri and tetrachloromethane. So what's going to happen? So this reaction subject to the radical formation. Generally speaking, in your radical formation reaction, you are going to go through 3 key steps. The first step called initiation. You are going to need to initiate a formation of your radical, and then propagation, produce more radicals, and then termination. If your radical they react with each other, you are going to terminate this reaction. So let's see. First step called dissociation. You must have a bond. The bond must be break up. If you have your chlorine molecule, this chlorine molecule is going to subject to the hydrolytic bond cleavage. Each of the chlorine atom going to retain its own electron. So you have 2 radicals, 2 chlorine atoms, they also 2 chlorine radical. This chlorine bond is broken up based on the homolytic bond cleavage. Chlorine bond, covalent bond is broken homolytically. The bond is the weakest part in the reaction mixture. So this will be your initiation. And then if you use heat or light, you heat it up, or you use the light. Normally we use the light. So the light or heat can provide sufficient energy for this bond cleavage of your chlorine to produce chlorine atoms. And then you use the single hooked arrow to show the electron movement. Again, each of the atom going to retain one of the unpaired electron. And then second step, so you have your hydrogen in your methane. So your chlorine has the chlorine atom, this one has 1 electron which is not paired. And then your hydrogen carbon, they paired hydrogen. So again, let's continue our lecture. Step 2, hydrogen atom abstraction. In the first step, dissociation, your chlorine atom is formed. This chlorine has 1 electron which is not paired. It's seeking another electron. So therefore, so your methane has a hydrogen. This hydrogen is going to break up. Hydrogen carbon bond will be break up homolytically. Your hydrogen bring 1 electron with it to form HCl bond. You see this is solid line. And then your methyl retain its electron to form a methyl radical. This is your propagation. So again, hydrogen atom abstraction. So chlorine radical abstracts a hydrogen atom from your methane molecule, forming a HCl, hydrochloric, hydrogen chloride in this case, and a methyl radical. Your methyl radical is going to be reacting in the chlorine in the following step. This step, you consider it propagation. So the methyl group, the methyl radical, reacted with your chlorine. Chlorine again has a weaker bond compared with carbon-carbon, carbon-hydrogen bonds. And then your methyl, this methyl tends to attract to your chlorine. So chlorine atom abstraction. So one of the chlorine bring one single electron to form a chloromethane. You see the black colored line? So this is a single bond, one electron from your methyl radical, another electron from your chlorine atom. And then the second chlorine atom becomes another radical. Again, this step is a propagation. The methyl radical abstracts a chlorine from chlorine molecule Cl2 to form a chloromethane and another chlorine atom, which is a radical. Chlorine radical again starts another propagation cycle. So your step 2, step 3 is going to be repeating. You repeat your step 2, step 3. And also we have something called the termination. If you have two radicals, when they are reacted with each other, they effectively stop the propagation steps. Therefore, you know that step as the chain termination step, such as you have your methyl radical, you have your chlorine atom, also another radical. This two is going to be bonded to form a chloromethane, covalent bond formed between carbon and chlorine. This is called the termination. If you have two methyl radicals, they can also react with each other to produce ethane. So this is another way to terminate your reaction. Chlorine atoms, they can also react to form a chlorine molecule Cl2. So that's the step of termination of the reaction. If you have a higher alkane, you can also go through this halogenation. Halogenation of higher alkane usually need the light. In our labs, we do use the light to initiate the chlorination of the higher alkane. Can be cycloalkane, can be a little larger N-alkane. For example, your cyclobutane reacted with your halogen chlorine. Under the light, you produce this chlorocyclobutane and HCl. So what's going to happen in this case? Are you going to form different molecules? So possibly no, possibly you only produce one type of molecule, because these 4 carbons connected to other 8 hydrogens. All these hydrogens actually they are equivalent to each other. So therefore you form this, I will consider it secondary. So carbon connected to the other 2 carbons, secondary molecule. If I have a normal butane, 1, 2, 3, 4 normal butane, in this normal butane, you see you have this carbon, which is only connected to another primary carbon. This carbon, these 2 carbon 2 and 3, they both are secondary carbon, meaning they have 2 hydrogens, and then you also have these 2 primary carbon, 3 hydrogens, totally have 10 hydrogens, 4 to 6, so 4 hydrogens, which are connected to the secondary carbon, 6 hydrogens connected to the other two carbons. What you should produce? You should produce at least 2 types of chlorobutane. You should have a primary, so 1 chlorobutane. The first carbon will be the hydrogen connected to the first carbon will be replaced, or the hydrogen connected to the second carbon will be replaced. You either form a primary or secondary chlorobutane. So halides can be primary or secondary. But what we see is 28% over 72%. So primary carbon you have 28%. The secondary replacement you have 72%. In the reality, that's what happened. But let's go back to double check. You have 6 primary hydrogen, 4 secondary. Theoretically, you should see this primary replacement should be 60%. Secondary replacement should be 72%, should be 40. However, we do see 28, 72. What's the reason? The reason again because of your secondary radical is more stable. Secondary radical is more stable than the primary radical. So that's why your secondary product, so 2-chlorobutane, has higher percentage, higher production yield. I do have a couple more reactions and related mechanism, so I'll leave it for everybody, so you take it home, practice it by yourself. And then we are also going to give you a little more about tertiary carbocation. If you can form a tertiary carbocation, so that product will be the major one. And then about bromination. Bromination refers to the alkane reacted with Br2 bromine. This reaction usually also requires light and high temperature. The reaction rate is also similar to the chlorination. Tertiary is more rapid, more reactive, and secondary and tertiary. So let's see what happened compared with these two. If you have your chlorination was found is an exothermic reaction. So your bromination was found to be an endothermic. So this endothermic reaction also is more selective. Very commonly used reaction normally to produce halides from your alkane is through the chlorination. As we mentioned, the positively charged ion and radical stability, they are related to the different types of carbocation. In general, the more stabilization, the electron stabilization, the charge delocalization, the more the charge is delocalized, the more the radical is delocalized, the more stable the related species is. Again, if you have carbocation, positively charged ion, if it's more stable, if it's more stabilized, so that species is more radical, similar for the carbocation. And also I have a couple more other chemical reactions. Ask everybody to confirm the radical formation procedure or the carbocation formation procedure. Again, I will leave this for everybody to study. I have two more tables. Summarize the functional groups. So functional groups in the alcohol and this related nomenclature. So for your study. Another, the last one, I think I do have one more slide. So give you the bond dissociation enthalpy. So bond dissociation enthalpy can help you to determine which one is more stable, meaning in the reaction that stable atom or molecule is not easy to be involved in reaction. The reaction rate may be slower down. So again, from today we concluded the chapter 4 about alcohols and alkyl halides, two different functional groups.